Hello, and welcome to another tutorial about deep rising effects. Yeah, so in this tutorial we're going to be looking at the granular particles. I just realized I haven't done any videos on the other solvers, so I'll be doing one on the grains. So I'll be starting with the arena solver, and then later on in another video I'll probably do the Proxima viscous jet solver into detail. So for this I'll just go into the basics and the settings of how to set it up. It's a bit different from the euphoric solver, so there's no meshing step and stuff like that. So I'll just set up a basic scene and show you how to the best workflow for this. So what I'm just going to do is add a plane to the scene. So the plane is triangulated. Don't forget to triangulate your geometry. So all geometry that goes into the engine needs to be triangulated. So I've got a triangulated plane, and I'm going to go to model, geometry, and sphere. I'm going to add a tessellation sphere because I need it to be triangulated, and just press OK, and that should be enough to get started. So I'm just going to scale up my grid just for better visual representation. Okay, so select the sphere, just put it above the plane. Go to the deep rising tab. So I assume you've got your deep rising set up like this. There's a configuration menu that comes with the plugin, so you should have something similar to this. So I'm going to use the shortcuts for this, but I'll open up the domain so you see what is happening. So just select the plane and click DR rigid object, and if you just click on this, it will update here. So we've got our rigid object plane. Click the sphere and click the granular object, it to go opaque. So, and we've got our object here, and you can see how many particles have been generated, which are 6,000. Okay, so that's the basic start. So if we hit the simulate button, nothing will happen. Okay, so sorry, actually 1 second, did I change the solvers? Oh, okay, so I'm using an old setup. I skipped a step there, sorry. So you need to change so by default if you click simulate, nothing will happen because it's on the euphoric solver. So make sure to go to solvers and switch to arena granular solver. Okay, okay, just for now. So okay, so sorry about that. So let me just do that again. So I'm gonna start simulating okay. So basic settings. So the thing you've noticed, if we go to VPR, for example, you can't see the particles. Okay, so it would be nice to see the particles while simming and testing stuff instead of just seeing the blue particles. So luckily it's possible. You can have you can preview your particles geometry. So what I'm going to do first is load in proxy. I'm going to use instances for the particles. So I'm just going to load in the object I'm going to use. So I've got a sphere. It's just a simple sphere. Okay, so pretty much tessellation. Then I'm going to scale this down to make sure your sphere is about 1 meter. So my sphere is about 1 meter in diameter. So I'm gonna do that. That's a good for most scenarios. Okay, so that's done. Then you need to use the fluid cache. So you see this big icon with the lightning sign on it, that's the cache. Okay, so what you need to do is select the cache, go to properties, go to instancing, click on instance generator. Oh, before you do that, so you click on the cache, so don't forget to do this. You need to go to preview and say attach PFX. That will attach a lightwave particle system to it. Okay, so once that's done, you select the geometry you want and just say particles. Okay, so they'll appear, but we need it to be a better representation of this, so it's going to say shaded solid. Okay, so done. That will allow us to preview our particles. Oh, oops, so I made a mistake there. Go back to sphere. What did I do? Okay, 1 second. Just I need to do that. Okay, there's a keyframe for the scale there. So yeah, so this is the cache. So you will get your cache there. So that's how you set it up. Okay, so once that's done, that's done. So I'm going to go to another scene that I've already set up. Okay, so this is the scene I have set up. So we're going to start from the very basics. So we won't really need the domain if the particles are already there. If once that's set up, we'll mainly be looking at the simulation panel. So what I've done is reset all the values. So I've left the time step the same 12 steps, etc. But what I've done is I've dropped the iterations to the most basic iteration. I've left the collision stiffness. We'll look at that. That's very essential. 1 minimum should be 1. I've switched off the static friction. I'll talk about that, and kinetic friction. I've left the dampening. Actually, I'll switch that off just to demonstrate. So the most basic simulation could be this. I've switched off everything. Gravity is the normal gravity, and I hit simulate. Okay. Or when you simulate, you will see the particles. But once that's done, you'll be able to see the solids. So I've already attached the instancing system to this, but you won't be able to see it during the simulation. But once the simulation is done, you can scrub through pretty easily with the instancing. So this is using the instancing. It's a pretty, so it's a transition is pretty transparent. So what we see is a very unstable simulation. We see particles going through the ground, they explode, they fly off into the distance, and that's normal. Okay, so the granular solver is not physics based, not physically accurate. Okay, it tries to be physically accurate, so it's not like your traditional physics engine like Bullet or NVIDIA physics. Okay, it uses something called position-based dynamics, so it emulates physics, and by using constraints, so it tries to keep the distance between these particles at a minimum. Okay, so in order to do this, it does this in iterations. So the lower the iterations, the less accurate the simulation will be. So the reason for the penetration is that one iteration is not enough to eliminate the iterations, and the collision stiffness also plays a part in this actually. So, but that's for extreme cases. I'll talk about that again. So I'm going to increase this to the default 6 might be the default, and I'm just going to say simulate again. So we should get a more stable simulation. Okay. So we've eliminated the explosion and the particles going through. There's probably a few particles going through, but we can fix that. Okay, so I'm going to say abort. Okay, and we can just have a look at this. So as you can see, the particles are not going through the ground anymore, and they're not really exploding anymore. They're obeying the laws of physics. You know, it looks more physically, like, I guess you could say, the Newtonian physics type of thing. Okay, so but we can actually tame this a bit more. As you can see, there's absolutely no friction. Everything just flies everywhere. Okay, and I guess if you wanted this look, you'd be done. Okay, but I suggest leaving the default velocity dampening on. Okay, this acts as artificial friction. So I'll talk about these other frictions and then velocity dampening. Velocity dampening is just artificial friction. This just kills the velocity over time, and it also helps put the particles to rest. So if I just do a simulate, we see how that looks. As you can see now, things are much more tame, and the particles are beginning to pile up a bit more. And I would say that looks a bit more natural, actually. Okay. Oh, and yeah, before I continue, I'll just talk about the timing of this. So this is just, appears to be slow in the viewport, but in reality it's actually in real time. So if you bake this out to 24 frames per second, you will get a proper simulation. So I would suggest, if you want to get something more realistic, just every once in a while, just bake out, preview your JPEG sequence at a full speed. Okay, so just to get the actual feeling of how fast the particles are moving with your settings. So they'll appear slower in the viewport, of course, due to the rendering. Sorry, wrong screen. Okay, so how does this look with instancing? Okay, more tame, and we'll begin to see piles. Okay. So, a very important thing about particles or grains in general in real life is that they form piles. That's a very important aspect of it. That's what separates them from normal, like particle systems. You begin to form piles, okay? So, a pile of sand, as you can see, we're beginning to form piles, but it's not the most impressive pile I've ever seen, okay? And the particles are behaving, you know, just like particles right now. Actually, they're just sliding off the side. They're not really behaving very grain-like, okay? So, we can fix that. So the first thing we're going to look at is static friction. Static friction is, I'm just going to put this to 0.1, is, actually let's put this as very extreme. I'm going to put this to 1 just to demonstrate. But lower values like 0.1, 0.1 to 0.5 should be enough. Is more like classic friction. So this is when two bodies are rubbing against each other. And so this actually has a physics equation behind it, plus the position-based dynamics. Okay, so this simulates real friction. So if I press, okay, tries to apply a real friction model on the position-based dynamics, shall I say. We will begin to see it behave even more. We'll get higher piles, okay? Okay. So, and you will notice that the particles, I will just demonstrate something else. So we see that the particles come down and they jump up actually, which actually indicates this friction. So that's like opposing forces. Now we didn't see that before, so that's due to the high static friction. So you can actually eliminate that by dropping the friction to a lower settings. But as you can see now, we're getting even higher piles. Okay? Which is the next best thing. But if you look at sand in real life, or actually if sand has been in real life, it's also got something called kinetic friction, okay? So what friction does, is parallel friction. Normal friction is parallel, whatever surface it's touching, so it will slow down or slow in whatever surface it is. Now kinetic friction, think about like perpendicular. It gets rid of perpendicular motion. So to the surface that it's going against, or against another particle, and this is all about physics, about strain. Strain is not parallel, so matrix mathematics stuff. But all that stuff is very heavy. So for position-based dynamics, it's actual approximation again. It's a very fast approximation. So I'm gonna switch off the static for this just to demonstrate what kinetic friction is. I'll put it to 1 and I will hit simulate, and you will see something very interesting when I switch this on. Okay, as you can see now that the particles are forming huge piles, and the particles have become very sticky. Not really sticky, but it's keeping its form more. Okay, you could think about this like really cohesive sand, for example. As you can see, the particles are sliding less down the sides because we're eliminating a big chunk of the kinetic friction, so the perpendicularness. That's what was causing the sliding particles to slide off the side. But in practice, you will need to use both kinetic to get more realistic results. Is to use kinetic friction and static friction. So here we get very stiff. Let me just play this. Very stiff granular simulation, so they'll probably stay there until the end, as you can see that. So the default values, if I put them back, are 1. They give decent granular simulation. Let me just do that. I do simulate. Okay, so we're getting the stacking of the particles. They're still sliding a bit down to form the type of piles we need. Okay, so we can tune these settings to get what we want. Okay, so let's just do that. 1 second. And boom. As you can see now, that's behaving like real sand, much better. And you can see we've got a nice pile. And the dampening also helps the particles come to a rest quicker. So if we switched off dampening, you would see the particles actually continue further along and the power will probably be a bit more shallow. Okay, and sometimes even with high iteration. So what we could do actually here is just increase this to 12. This will also increase the accuracy of the simulation to make the particles more stiff. I guess I'm doing 12. I need to be slower, of course, because it's doing each step 12 times, but you will get more realistic results. Okay, so the simulation will also be stiffer. Okay, so if we press play, we get that, which is a much better representation of the particle. So this is 12 iterations. Okay, so that's about it, but I will talk about one more thing, the collision stiffness. So sometimes you will get particles that will penetrate through your geometry for different reasons, awkward angles, maybe it's too fast, etc. So one way obviously is just to increase the accuracy, but sometimes that's not enough. So in most cases, the collision stiffness of 1 is more than enough. But if you're seeing particles go through, you can always crank it up. So if I was to crank this up to 2, you can have a look. There's no penetrations here, but also having a higher collision stiffness will change the behavior of the simulation as well. Okay, but it should also fix any additional leaking particles if you've got any. Okay, so okay, that's it's done. So yeah, so there's no real difference here. But if you were seeing any particles, oh, actually this eliminated the bounce. It was really a bit bouncy there, so increasing the collision stiffness made it less bouncy as well. So there's that as well. Okay. So yes, so that's the arena granular solver, and it's a bit straightforward compared to the euphoric solver. So it takes less, it's less technical, I guess. And the results are pretty straightforward, and the meshing is straightforward. You don't need any tools. You don't need to export. You just instance everything, and you can actually bake this out to Alembic, since the particles don't change in every frame, and then you can just load them back into Lightwave actually, which is good actually. Yeah. So that's it. Thank you for watching. I'll see you in the next video.